Good day, everyone. To begin, let me give you a quick overview of the tasks I've been assigned to report on. So this presentation slide focuses on electrical code standards related to conduit and tubing field, specifically how much of a conduit cross-sectional area can be occupied by conductors. The guidelines are based on standards such as those found in the National Electrical Code or NEC or similar regulatory frameworks. So here are the key points include conduit field limits, jamming risk, special consideration, conductor types, and lastly, ampacity derating. So these standards ensure that electrical installations are safe, efficient, and compliant, reducing risks associated with improper wiring, physical damage, and thermal overload. Okay, let's begin with slide 1. As you can see, this outlines the specification of a marine cable. This slide defines a specific type of cable. A marine cable, it is made with PVC insulation, a PVC sheet, and has a copper braid. This is likely used for electrical system on boats or in wet location. Slide 2. Conduit fill percentage. This table provides rule for how much space inside a conduit. The pipe that holds wire can be filled with conductors. A keynote, FP-in1, explained that these rules assume a standard wire pull. For difficult pulls with many bends, you might need to use a larger conduit or fill it less. Slide 3. Avoiding jamming in raceway. This slide warns about jamming, which can happen when pulling three wires into a conduit. Jamming is most likely if the ratio of the conduit inside diameter to the wires outside diameter is between 2.8 and 3.2. The risk of jamming is very low when pulling 4 or more wires. Slide 4. Important notes on conduit fill. Part 1. Note 1. For the maximum number of same size, wires refers to Annex C. Note 2. These fill rules are for complete conduit system, not just for short pieces used for physical protection. Note 3. Grounding wires must be included in your conduit fill calculation. Slide 5. Important notes on conduit fill Part 2. Note 4. Short conduit section nipples under 600 mm can be filled up to 60% of their area. Note 5. For special cables like multi-conductor or fiber optic, use their actual dimension for calculations. Note 6. For mixes of different wire size, use actual dimension of the provided table. Slide 6. Important notes on conduit fill Part 3. Note 8. For bare conductors, use the dimension given in the code tables. Note 9. A multi-conductor cable, like an extension cord, is treated as a single conductor for fill calculation. If it's an oval shape, use its widest diameter for the calculation. So here in slide 7, conductor dimension and conduit sizing. Note 10. The standards diameter values in the tables are worst case scenario for standard stranded wires. If you know the exact smaller dimension of your wire, you can use them. Note 11. The conduit sizes in the tables refers to the internal diameter. If a conduit is sized by its outside diameter, its inside diameter must be at least as large as the value in the code tables. In slide 8, ampacity and conduit fill. The current carrying capacity, ampacity of wires listed in chapter 10 assume a specific conduit fill. If you put more wires in a conduit than specified, you must reduce the rate, the ampacity of those wires to prevent overheating. In slide 9, conduit fill table. So as you can see, this image shows a reference table used in electrical work to determine the maximum number of wires conductors allowed inside different types and size conduit raceway. The goal of this table ensures conductors don't take up too much space inside the conduit, which prevents overheating and make it impossible to pull wires safely. This table is based on strict code limits for the cross-sectional area of the wires, 40% fill for over 2 wires. Slide 10. These tables are from the electrical code and show how much space wires can take up in a pipe conduit. Purpose: to prevent overheating and damage by limiting the amount of the area the wires fill. K-limits: the maximum allowed area for the wires depends on the number of wires. 40% fill for over 2 wires, standard installation. 53% for 2 wires, 60% fill for 1 wire. How to use: find your conduit type, example PVC, its size, example 1 inch, and the required fill percentage to get the maximum total area your conductor can occupy. In slide 11, as you can see, this table lists the size and area for many types of insulated electrical wires. Example: THHN, RHH. Purpose: the purpose of this table is to find the exact cross-sectional area of the wires you plan to install. Application: you need this area to calculate the total space your conductors take up, ensuring they do not exceed the maximum fill limits, like 40% rule, of the conduit they are being pulled into. In slide 12, this is the continuation of slide 11. Purpose: to find the exact cross-sectional area of the wires you plan to install. Application: you need this area to calculate total space your conductors take up, ensuring they do not exceed the maximum fill limits, like 40% of the conduit they are being pulled into. In slide 13, this is the continuation in the previous slide. Purpose: it lists the cross-sectional area and diameter of individual insulated electrical wires based on their size and insulation type. Application: electricians use these precise area values to calculate the total space required by all wires in run and ensure that they comply with strict conduit fill limits, like 40% found in the other tables. Slide 14. Continuation with the previous slide. Purpose: it lists the cross-sectional area and the diameter of individual insulated electrical wires based on their size and insulation type. Application: electricians use these precise area values to calculate the total space required by all wires in a run and ensure that they comply with the strict conduit fill limits, like 40% rule found in other tables. Slide 15. This image displays the table, a compact aluminum building wire, nominal dimensions, and areas for Chapter 10 of an electrical code. Purpose: this table specifically provides the dimension and area for compact aluminum conductors, which are often used in commercial and industrial wiring. This is necessary for accurate conduit fill calculation. Application: these specific values are critical for calculating the total area of the wires and ensuring it does not exceed the 40% maximum fill limit of the chosen conduit. So here in slide 16, this table lists technical data for bare and insulated wires, coppers, and aluminum. Purpose: to provide exact area, diameter, and DC resistant values. Application: these values are essential for calculating voltage drop and for precisely determining the conduit fill area for certain conductor types. In slide 17, table AC resistant and reactance. This is a highly technical table used by engineers for calculating electrical performance, particularly in three-phase, 60 Hz system operating. Purpose: to provide the alternating current, AC, resistant, and reactance values in ohmega for various sizes of insulated conductors, copper, and aluminum. Application: these values are essential for accurate voltage drop and fault current calculation in AC power system, taking into account the type of raceway, steel conduit, PVC conduit, which affect the resistance T. Table 10.1.110 Conductor Stranding. Purpose: these simpler tables list the stranded number of strands for different sizes of copper and aluminum conductor. Example: Class B, Class C. Application: Knowing the number of strands is important for selecting the correct connectors and for understanding the flexibility of the conductor during insulation. Slide 18. This table A set the maximum voltage, current, and power limits for power supply classified as Class 2 or Class 3 circuits. Purpose: to define the electrical threshold for these circuits, which ensures they are considered safe, low risk of fire or shock, and can therefore use simpler low-voltage wiring methods. Key idea: the limits are strictest, lowest current or VA when the power source does not require overcurrent protection. Slide 19. This table B set the maximum voltage, current, and power limit for power supplies classified as Class 2 or Class 3 circuit that use DC power. Purpose: to define low power threshold that makes these circuits safe and allow them to wire with simplified low voltage method. Key idea: the limits are strictest when the source is designed without required overcurrent protection or OCP to guarantee string safety. Slide 20. This is the last slide of my report. This table sets the maximum voltage, current, and power BA limit for power limited fire alarm or PLFA circuits. Purpose: to define the low power threshold that ensure fire alarm wiring is safe and can be installed using simplified methods. Key idea: limits are separated for AC and DC power and are strictest when the source is designed to be inherently limited, no external overcurrent protection needed. To end my report, I want to thank you guys for your time and listening. I hope this video report has effectively highlighted why the Pec Standard is critical for ensuring safety and quality in our industry. Thank you and goodbye!